Here I've got another nice integral from the integral suggester, which will involve a lot of nice techniques that will provide a really good review for integration. Okay, so let's see what we've got. The integral from 0 to pi over 2 of the arctan of sine of t over sine of t dt. We're going to use the following two integrals as tools, which we'll evaluate on their own just because they're a little bit messy. The first of which is the integral from 0 to 1 of y to the 2n times the natural log of 1 plus the square root of 1 minus y squared dy. So that's a little bit of a mouthful. And this could be generalized for non-even numbers up there, but we'll only need it for even numbers up there. So that's equal to 1 over 2n plus 1, 2n minus 1 double factorial. So what I mean by that is the descending product starting at 2n minus 1, but skipping all of the even numbers. So for example, 7 factorial would be 7 times 5 times 3 times 1. And then we have in the denominator 2n double factorial. So that's like the product of all of the even numbers up to 2n. Next, that's multiplied by pi over 2. And then we have minus 1 over 2. That should be n plus 1 squared. So that's our first integral that we'll calculate. The second one will be the integral from 0 to 1 of y to the 2n times the natural log of y. That one's a little bit simpler. That just gives us negative 1 over 2n plus 1 squared. Okay, so let's get to this first tool, and as it involves an inverse function, we'll use the fairly standard strategy for integrals involving inverse functions, and that is integration by parts. So we will set u equal to the inverse function, and then dv will be all of the rest. And that's because generally when we have an inverse function, finding the derivative is much easier than finding the antiderivative. Okay, so with that substitution, what does that give us? So du, which I won't calculate with all of the details, you have to use the chain rule along with like a bunch of other standard derivative rules, simplifies down to the following object. So we've got 1 over y minus 1 over y times the square root of 1 minus y squared dy. So that's our du term. So like I said, if you need to pause and practice that derivative just to convince yourselves that that's the case, maybe go ahead and do that. Okay, but then taking the antiderivative is fairly straightforward. We can just use the power rule. So we call that dv, so we'll say that v is equal to, let's see, it'll be 1 over 2n plus 1 times y to the 2n plus 1. Great. And now those two parts set us up really nicely for integration by parts. So let's see what we'll get. So we'll have u times v, but then we need to evaluate that at 0 and 1. So I'll just write that as u times v evaluated from 0 to 1, and then point out that each of those will give us 0. So obviously if we evaluate v at 0, we get 0 because we have a y here. This is a positive number. And then u evaluated at 1 will give us 0 because we have the natural log of 1. So I'll just maybe not do all of that on the board. I'll just say that all of this turns into 0. So that's a nice simplifying effect. Okay, nice. And then we'll have minus the integral of v du, and that integral is from 0 to 1. That's because of the integration by parts formula, which goes like this. The integral of u dv is u times v minus the integral of v du, just to recall that. Well, I'll take this minus sign inside of the integration by parts formula and have it switch the order of subtraction just to keep everything kind of nice. And that'll give me 1 over 2n plus 1. So that's taking this constant out. And then I'll have the integral from 0 to 1 of y to the 2n over the square root of 1 minus y squared. That's what we get from this term. Recall that we're changing the order of subtraction because of our minus sign built in here. And then finally, minus y to the 2n dy. So that's what we have. Now I'd like to integrate out the part that's fairly simple, just so that we can take care of that on its own. So let's notice that this guy right here is just another copy of 1 over 2n plus 1 because of the power rule. So that's going to give us something that looks like the integral from 0 to 1 of y to the 2n over the square root of 1 minus y squared dy. Then, like I said, minus 1 over 2n plus 1 quantity squared from integrating that y to the 2n out. Okay, so next up, we'll want to do some sort of substitution so that we can simplify this guy. But what kind of substitution jumps out? I would say a trigonometric substitution, given that we have this square root of 1 minus y squared term. So let's set y equal to sine theta. That tells me that dy is equal to cos theta d theta. Furthermore, I have the square root of 1 minus y squared is also equal to the cosine of theta, just by the Pythagorean identity. Then if y is equal to 0, theta is equal to 0. So that's how the bounds of integration change, or the bottom bound of integration. And then if y is equal to 1, theta is equal to pi halves. So that substitution will allow us to rewrite our y integral as a theta integral. So that'll leave us with the integral from 0 to pi over 2 of sine to the 2n theta d theta minus 1 over 2n plus 1 all squared. So notice the cosine and the cosine canceled. Okay, so that's starting to look good. Let's maybe bring that up and then we'll work towards the end. Okay, so this is where we ended up. This first big integral, which will be a tool for our major goal, is equal to 1 over 2n plus 1 times the integral from 0 to pi over 2 sine to the 2n theta d theta minus 1 over 2n plus 1 squared. I think I forgot this coefficient in the last step on the last board, but we fixed it. Okay, now we can use a power reducing formula for sine. So I'll let you guys look that up. I think we've used that on the channel before. I won't derive it here. So we'll use a power reducing integral for the sine function. So I think given that we're doing this thing that is quite complex, just using this without maybe proving it is okay. So after one step, this is going to look like 1 over 2n plus 1. And then we'll have 2n minus 1 over 2n times the integral from 0 to pi over 2 of sine of 2n minus 2 theta d theta minus, and then we have this thing that's just coming down for the ride. So that's what we have after one step of this power reducing formula. So let's maybe write one more step of the power reducing formula, and then we can see where we're going. So that'll be 1 over 2n plus 1. That's just coming down. 2n minus 1 times 2n minus 3 over 2n times 2n minus 2. And then we'll have the integral from 0 to pi halves of sine of 2n minus 4 theta d theta minus this thing that is just omnipresent. Great. Now we can keep applying this over and over and over until we get sine to the 0 power, but then we'll just have the integral from 0 to pi over 2 d theta. But that just gives us pi over 2. And we'll be left with exactly what we want in the numerator and the denominator here. So maybe if you want to work out the rest of the details, I urge you to, but I think this is a good place to stop for this integral. Okay, so now let's move on to the second one. So we just got done deriving this identity, and now we're ready to look at the second one. We could do this second one with integration by parts as well, but in fact, it's a little bit simpler to do it with a substitution. So the substitution that we'll do is y equals e to the u. Okay, so let's notice that that means that dy is equal to e to the u du just by taking the derivative there. Okay, then furthermore, the natural log of y is just equal to u, and then our bounds of integration, let's see what we have for those. So if y is approaching 0 from above, then that means u is approaching negative infinity. And then if y is approaching 1 from below, that means u is approaching 0. Okay, so all of this will build our translation from a y integral to a u integral. So let's see what we have. This will be the integral, like I said, from minus infinity up to 0 of, well, we have a u from this natural log, and then we have an e to the 2n u from this, and another e to the u from this. So in the end, we have u times e to the 2n plus 1 times u du. Great. And from here, we could maybe use integration by parts because we have a polynomial times an exponential function, but we might as well use this DI method or tabular integration just to keep it shorter. So let's do that. So let's see, we'll put a u here, and we'll put an e to the 2n plus 1 u here. We'll take derivatives down this column, so that'll give us a 1 and a 0. Take antiderivatives down this column, so that'll be 1 over 2n plus 1 e to the 2n plus 1 times u. And then finally, 1 over 2n plus 1 squared e to the 2n plus 1 times u. And then we match on the diagonal and alternate the signs. Okay, so that tells us that this thing looks like 1 over 2n plus 1 u times e to the 2n plus 1 times u, evaluated from minus infinity up to 0. And then minus 1 over 2n plus 1 squared e to the 2n plus 1 times u, evaluated at minus infinity and 0. Obviously, when I say evaluated at minus infinity, I mean we're taking the limit. Okay, so let's see. If we plug 0 in here, we'll get e to the 0, which is 1 times 0, that's 0. If we let u approach minus infinity, then the exponential thing will win, and so this whole thing will tend off towards 0. Okay, then similarly, the minus infinity here will go towards 0, and we're just left with the e to the 0 term, which is 1, and that gives us minus 1 over 2n plus 1 squared, which is exactly what we wanted from over here. Okay, now we've got both of these tools in place, and we're ready to attack our main goal. We just finished up building our two tools, and now we're ready to look at our goal integral. And we'll start off with a substitution. And that substitution will be setting x equal to sine of t. But let's notice that that means t equals arc sine of x, which means dt equals 1 over 1 minus x squared. That's in a square root dx. So that gives us all of the parts to make our substitution from our t integral to our x integral. Let's see what that gives us. So we'll have the integral of the arc tan of x over x times the square root of 1 minus x squared dx. That's what happens there. Then furthermore, what happens to the bounds of integration? So when t equals 0, x equals 0, and when t equals pi over 2, x equals 1. So now we have the integral from 0 to 1. Great. Now we'll use the fact that the derivative of the inverse tangent is 1 over 1 plus x squared in order to translate this into a double integral. So I'm going to translate this into the integral from 0 to 1, and then the integral from 0 to x of 1 over 1 plus y squared times x times the square root of 1 minus x squared dy dx. So it's something that looks like that. So notice our innermost integral only depends on y. When we integrate that out, we get the arctan of y. Evaluating at x, we get this. Evaluating at 0, we get 0. So we're good to go there. Okay, so now I'm going to take this iterated integral and write it as a double integral. So this is going to be the double integral over a region which I'll call D of this same function. So I'll write it as 1 over 1 plus y squared times x times the square root of 1 minus x squared, and then dA. And now let's get a SketchUp of this region. So let's see, the x values are going between 0 and 1, and then the y values are going between 0 and x. So that means we need the line y equals x here, which is about like that. So that tells us that our region D looks like this. Okay, so that's good to know because now we can reparameterize this in the opposite order. So let's see, y will go between 0 and 1, and then x will go between the line x equals y and the line x equals 1. So that's how I like to think about that. So that's going to turn this into the integral from 0 to 1, the integral from y to 1 of 1 over 1 plus y squared times x times the square root of 1 minus x squared, and then we'll have dx dy. So we've changed our order of integration there. Okay, nice. So now let's maybe bring that up and then we'll keep going. So we got our goal integral down to the following iterated integral, which I've rewritten just a little bit from what we had on the bottom of the last board. And now we're ready to tackle this innermost integral, which will use a similar strategy to what we did in one of the last steps, and that is trigonometric substitution. So let's say x will be equal to sine theta again. This is obviously a different x and a different theta from before. That means dx is cos theta, and that means the square root of 1 minus x squared is equal to cos theta as well. I forgot a d theta here. Okay, so that's looking good. That's going to allow us to rewrite this as the integral from 0 to 1. And then inside of that, the integral from something to something. I'm not going to worry about changing the bounds of integration because this time I'll change back to my original variables of, let's see what cancels out. So the cosine and the cosine cancel and we're left with 1 over sine, but 1 over sine is the same thing as cosecant theta d theta. And then our dy integral is outside of the whole thing. Now, the integral of cosecant is a little bit tricky, but it's generally taught in a calculus class, so we won't derive that. We'll just jump to what it is. It's something like negative the natural log of cosecant plus cotangent. So let's write that down. We have this is equal to the integral from 0 to 1. Then, like I said, negative the natural log of cosecant theta plus cotangent theta. And then I left out my 1 over y squared here, so I've still got my 1 over y squared here. This needs to be evaluated from something to something, which we'll take care of when we switch back to our other variable. And then we have dy. But now we can switch that back to our original variable fairly easily. Let's recall that cosecant is 1 over sine, so that makes this equal to 1 over x, given this right here. And then cotangent is cosine over sine, so that gives us the square root of 1 minus x squared over x. So let's write that as the square root of 1 minus x squared over x. So that's looking good. And then finally, we can replace these theta numbers with x numbers. So that's going to be evaluated from x equals y up to x equals 1, where those are substituted back in. So let's notice that x equals 1 will give us 0 upon evaluation because we'll get the natural log of 1, which means x equals y is the only thing that's going to give us anything. It's on the bottom end point. That means that it will cancel this minus sign due to the subtraction that's built in, and that'll leave us with the integral from 0 up to 1 of, let's see, it's going to look something like this, the natural log of 1 plus the square root of 1 minus y squared over y all over 1 plus y squared dy. So that's what we're ending up with now. Okay, so now we'll move to probably the last chalkboard, but before we do that, I want to point out that we can split this natural log in the numerator up. This naturally splits into the natural log of 1 plus the square root of 1 minus y squared minus the natural log of y, just by natural log rules. So on the next board, we'll start with that split, having split the integral into 2. Building off what we had on the last board, we have to tackle these last 2 integrals. We're going to do those via series. So let's notice this 1 over 1 plus y squared can be thought of as a geometric series where the common ratio is negative y squared. We're within the bounds of convergence, so we're okay there. So I'll do that for each of these separately. So I'm going to write this as the sum as n goes from 0 up to infinity. I'll take my minus 1 to the n out. And then I'll have the integral from 0 to 1 of y to the 2n times the natural log of 1 plus the square root of 1 minus y squared dy. So that'll be this guy. Then we'll have something similar for this guy. So maybe I'll put those two sums together. So that'll give me minus the integral from 0 to 1 of y to the 2n natural log of y dy. Okay, so let's maybe put some big parentheses in a different color here to see exactly what's going on. So that's the kind of situation that we have. But inside of these orange parentheses are exactly our 2 tools. But let's notice that if we take this first and subtract the second, this extra little term cancels, and we are only left with this big stuff right here. So that means all of this will collapse to the sum as n goes from 0 up to infinity of minus 1 to the n over 2n plus 1, and then we have 2n minus 1 double factorial over 2n double factorial times pi over 2. And then while we're at it, let's take this pi over 2, and since it's in all of the terms, factor it out. So here we've got a pi over 2. Now we can look at this sum, and this sum is actually something that we've used a closed form of in a previous video. It's a fairly recent video. If you guys can find it, maybe post the link and I'll pin that comment. So this is the expansion of the inverse hyperbolic sine evaluated at 1. So I'll write that down. So this is arc sine h evaluated at 1. So inverse hyperbolic sine. But inverse hyperbolic trig functions can often be written in terms of logarithms, and this is the case here as well. This is equal to the natural log of 1 plus the square root of 2. And I won't go through those derivations carefully because this is already turning out to be a fairly large video. So putting this all together, we'll see that in the end we have pi over 2 times the natural log of 1 plus the square root of 2 as the value for our goal integral. And that's a good place to stop.